Okay, so we'll get started, and this is the last class. So hopefully, like you guys learn a little bit something like this semester. So I like to talk about something is pretty useful. Actually, it's kind of weird that like we only talk about this last moment, but I guess like in any case probably it won't be too late, but and also like you probably will come across that like as you go along reading paper and so on. So I like to talk about conjugate prior and also the exponential family. So let's start with the conjugate prior. So the idea is actually very simple. So think of like the problem that we have the Bayesian inference. Either you are doing Bayesian or you are doing map estimation, maxima posterior estimation. So in those cases, you will have prior and also have the likelihood, right? So basically, for example, if I consider map, if I want to try to like have some parameters that I'm going to estimate. So let's say I parameter theta, and basically I have the likelihood is that P is given theta, and I have P theta is the prior. So I want to get a map estimate of theta. That's basically argmax of px theta multiplied by theta, maximized with respect to theta. And again, this is the likelihood, this is the prior. So what do we mean by conjugate prior? Is like, let's say if we have some model for the likelihood, say the model for likelihood, this can be like we're estimating the mean, and this can be like Gaussian distribution, let's say. And we want to, there's no particular reason what kind of prior we should select, but just for convenience, it would be very nice to select the prior that have a form like kind of similar as the form of the likelihood, so that when we multiply these two together, they still have the same form, basically preserve the form of the likelihood. And in that case, we call that prior is a conjugate prior of this like likelihood function. So let me give you a concrete example. I guess this will be very clear after an example also. So let's consider like a again we have an example of flipping ancons, tossing ancons there, and we try to see like and let's say the outcome of tossing these ancons, I have k hats there, right? So and then if I just look at the likelihood, let's say I have the theta, in this case is the parameter we want to estimate, is just, let's say call it Q, is the probability of getting hat. So in that case, the likelihood function will be just a binomial distribution, right? And the probability Px given theta therefore will be just like binomial of k with ancons and the probability, let's say Q, and that's basically say nq q to the k 1 to q minus n minus k, right? So now if I want to have a map estimation, I should multiply by some p theta. So I want to have like multiply by this theta. Oh, okay. In this case, what are the variables here? The variables will be q, right? Or like theta is basically q, right? Okay, maybe I just write q here. I am trying to estimate the q, right? So I want to multiply this pq with this guy. Afterwards, still have like a form similar to as like this one. So then by inspection, we would like to have pq have a form something like q to the a, like 1 minus q to b, something like that, right? Something like this. And it turns out like the distribution for this guy is called beta distribution, and it's actually defined as a beta Q A B. Instead of like Q to the A, actually the convention is Q to A minus 1 and 1 minus Q to the B minus 1. And of course, you will have some normalization factor here. So in general, this won't normalize to 1, right? So if I take integral with respect to Q, this one won't be equal to 1. So we need to normalize that. And the normalization factor turns out to be like this: gamma A plus B over gamma A and gamma B. So where this gamma is a special function, the special function gamma function that is given by like this. Actually, like this form is not extremely important. I mean, in the sense that I don't remember it most of the time. I mean, I just need to dig it up. But the important part is that like notice that the gamma function have a very nice property. Basically, gamma c will be equal to c minus 1, I think it's c minus 1, right? Multiplied by gamma c minus 1. So you can easily show this. So let's try to show this. So I have gamma c here is equal to 0 integral x c minus 1 exponent minus x dx. And so I can do an integration by part, and this will be where's that? Minus 0 infinity c minus 1. I'll absorb this exponential minus x inside, so I have that. Therefore, I have a minus sign out here. So now I can use integration by parts. It's like that. Minus x 0 to infinity plus I have e minus x. Then I should take derivative of this guy. I have like c minus 1 coming down here, x c minus 2 dx, like this. But if we look at this guy, the form this guy is exactly equal to this. It's just equal to gamma c minus 2. Gamma c minus 1, right? Because this is c minus 1, this is c minus 2. C minus 1 corresponds to gamma c here, c minus 2 gamma c minus 1 here. And for this guy, you can check like for both upper lower limit is equal to 0, so this is gone. So therefore, like we have this shown here. So and because of this, it is very nice. Like in particular, when c is an integer, then apparently you have gamma c is just equal to c minus 1 the factorial. Of course, we need to show that like gamma 0 is equal to, because we can just use this equation multiple times, right? Or like maybe I go a little bit step by step. I have like gamma c equal to c minus 1 multiplied by gamma c minus 1, then therefore is equal to c minus 1 multiplied by c minus 2, gamma c minus 2, and so on and so forth, until c minus 1 multiplied to up to gamma 0. But for gamma 0, or maybe I can stop with gamma 1, up to gamma 1, and gamma 1 is just equal to 0 to infinity exponential minus x dx, and if we take the integral, it's just equal to 1. So therefore, like we have like gamma c is equal to when it's integer, it's just equal to c minus 1 factorial. So in any case, maybe I should go back to the conjugate prior. So therefore, like what we show here is that like for binomial distribution, the conjugate prior of this binomial distribution is the beta distribution, is this one here. And let's just try to do a couple exercise to get familiar with the beta distribution. And also, like I want to say, like again, like this kind of equation is very helpful, very useful. as you can see, like for example, if I try to compute the mean and variance of the beta distribution, I don't need to really go through the integral, but I can take advantage of this kind of equation here. So for example, let's see, let me start with just trying to compute the mean. Let me start a new page here. So let's say if I have beta, right? Again, let's say the parameter for beta is a and b here, and I want to compute the mean, then it will be simply like this, right? Oh, by the way, I should emphasize the range of the beta distribution, right? The range of Q here is basically from 0 to 1. So that matches with what we're trying to estimate, right? Because theta here is the probability here. We expect this is a probability, is a discrete probability. So a probability mass function, it can go only from 0 to 1. So yeah, therefore this beta function actually it's here I was supposed to define it only from 0 to 1. Okay, so go back to here, if I try to compute the mean, let's say the mean for that particular parameter a and b here. So remember that we have the beta distribution have a format something like that, gamma a plus b over gamma a, gamma b, and then this is x to the a minus 1 and 1 minus x b minus 1, right? And this is beta x given a and b. Now multiply by x here, then I have x absorbed to here, right? So then basically I can change this from a minus 1 to just a. So I integrate this dx here, 0 to 1. So as I said, I don't need to actually integrate this because I can, okay, first I pull this out. This is gamma a plus b over gamma a, and gamma b, this is just constant with respect to x. And for what's inside here, you see this is actually correspond to, okay, this will have a very similar form as a beta taking a parameter a plus 1 and b, right? And I know that if I integrate this with some missing parameter, what I mean, if I have gamma a plus 1 and gamma a plus 1, gamma b, if this whole guy here, I should integrate up to 1 because this absorbing this guy into here basically is a beta distribution. If I integrate over all possible x, you should integrate to 1. So therefore, it means that if I just integrate this guy, it will be just inverse this guy, right? Inverse this normalization factor here. So therefore, this is actually equal to this one here. Or maybe I write it more nicely. So therefore, integrating this guy is actually will give me, let me just gamma a, gamma b, and this will give me gamma a plus 1 plus b, and this is gamma a plus 1 and gamma b. Okay. And then this got cancelled, right? And now we can take advantage of the formula we have. Remember that gamma a plus 1 plus b should be just equal to a plus b multiplied by gamma a plus b. So therefore, I have this gamma a plus b got cancelled, so this will get a plus b remaining, and also this got cancelled. I will only have a. So therefore, the expected value will be just a over a plus b for beta distribution. The mean is just a over a plus b. It's very simple. And similarly, I can try to compute the variance. For example, compute the variance directly is a bit more complicated. So the variance will be like that, right? A squared minus a over a plus let's see, times like this, right? This will be the variance. Because I know the mean is already this guy here. But of course I can also I also know that like variance also is equal to expectation x squared minus expectation x squared. So it actually will be simpler if we first compute expectation x squared instead, and then I just compute variance as expectation x squared minus the mean square. So for expectation x squared, we can do the same thing as we just did, right? So it's basically equal to x squared times beta. Again, it's like gamma a plus b over gamma a gamma b multiplied by x to the a minus 1 minus x to the b minus 1 dx, right? Now, like the previous case, I here I can pull it out, and this guy can absorb into here. So this correspond to integrating this correspond to 1 over the normalization factor of like a plus 2 and b of of the beta distribution with parameter a plus 2 and b. So therefore, like it's be equal to gamma a plus b over gamma a gamma b, and then this one, as I said, like the parameter should be gamma a plus b plus 2. This is gamma a plus 2 gamma b. So just like what we did earlier, so we can take advantage that like gamma x is equal to x minus 1 times gamma x minus 1. So this guy, these two, okay, basically this guy can be written as a plus b plus 1 times a plus b times gamma a plus b, something like. So I have gamma a plus b cancel. So what I have below, therefore I have just a plus b plus 1 a plus b, and for about gamma b got cancel, and this I have a plus 1 and a, something like that. And that's basically expectation x squared. And just using this equation, eventually you can substitute everything, and you get like square minus expectation x square, that after some steps will be just equal to a plus b square a plus b plus 1. So I just want to say like this kind of trick is very helpful. Like you don't actually need to do the integral, but oftentimes because you know the normalization factor of the distribution, then if you just ignore the normalization factor and compute the integral is basically equal to 1 over that normalization factor of that distribution, and you can just look it up what is the form of that normalization factor, like in Wikipedia, and then you can compute stuff. Of course, you can probably pick up the mean and variance directly from Wikipedia, but in general, this you can compute more complicated stuff. Like for example, like you can compute like x cube and x fourth, like apparently, and expectation x cube, expectation x fourth, like for example, all the moment, and can be computed pretty easily this way. So and this is the mean and variance. By the way, like let me also compute the mode of the beta distribution. The mode for the mode of beta, basically the peak, that basically will be just I'm trying to see where the distribution will have the slope is equal to 0, so I can just take partial derivative with respect to x is equal to 0. So that actually will give me something like a minus 1. Let's see, what's that form again? So I can because it's taking part. Let me copy the beta distribution again here. Gamma a plus b gamma A, gamma B, xa minus 1, 1 minus xb minus 1. So this is, I take partial derivative with x like this, I can ignore that. Like for this guy, I have a minus 1 xa minus 2 times 1 minus xb minus 1 multiplied by plus, let's see, yeah, plus b minus 1, 1 minus x b minus 2 xa minus 1. I have something below, it doesn't matter, I don't care, and the whole thing is equal to 0. So I just need to care about the numerator. So this is like x a minus 2, 1 minus xb minus 2 times a minus 1 times 1 minus x plus b minus 1 times x is equal to 0. So you get basically either x is equal to 1 or like 0. Those extreme cases, kind of trivial case, not typical, is not interesting. So for this guy is equal to 0, basically you get like x is equal to a minus 1 over a plus b minus 2. That's the mode for the beta. And let's see, what was next? Oh, okay. So next thing I want to see is, okay, we show that the beta is the conjugate prior, right? Now let's look at actually if we have the posterior, exact posterior will be like what? If we have the likelihood is binomial and prior is the conjugate prior, basically the beta prior, then so let's look at, like, I have QXAB, that I have as I said, like a binomial prior, sorry, not binomial likelihood. So it's like, let me write one more step. X given Q and P, Q given AB, right? Something like that. And we said like this is like binomial, right? And this is the prior, the conjugate prior. That's the beta. And this beta have a form that like Q to the A minus 1 and 1 minus Q B minus 1. Oh, it's okay. Oh, okay. Yeah, that's fine. So so this guy here, the binomial is I have what?
What is this?
This is, so we have binomial beta. We are talking about conjugate prior, basically. So if you have a binomial distribution,
This is new.
yeah, this is new. So we go back to, okay, sorry, I have someone coming in. Let's review a little bit again. So we have someone is, let's say the con problem again. We told a con like n cons and k hats here. So we try to estimate the probability Q there. Let's say we have like the Q is like the probability of hat there. So then like the likelihood itself is like just a binomial distribution, right? Like this guy, right? The probability of Q will be like this. Like just Q to K 1 minus Q, something like that.
An experiment.
Yes, an experiment. K is like we have K hat. That's the outcome.
Oh.
So and then we want, this is just the likelihood, right? So if we want to do Bayesian of like or maximum a posterior estimation, so we should multiply with the prior as well. So we want to pick the prior, so you can pick any prior. I shouldn't say you can pick any prior, but for practical purposes, you want to pick prior for conveniences that this has the same form as the likelihood. I mean, those cases we call it conjugate prior.
How to calculate the prior?
Let's say like what kind of prior we should pick first. Like you multiply this guy with something else, right?
Yes, that's right.
And we want to multiply this guy after multiplying it still have form similar to that. So to do that, like we can pick a prior. For example, like this is have a probability Q to
How we decide a prior, something like that?
This is just a okay. You pick this just out of convenience. I mean, like you can pick any form of the prior, right? So you can pick any form, but if you pick the form is totally does not match with this guy. For example, like I have Q is a distribution. For example, like if I pick Q to be some really weird form, for example, I pick Q to have some triangle form, like for example, like this. Whatever I say, this is my prior Q. This is valid, right? This is a distribution for Q. But the problem, if I pick this, I try to multiply this guy with this guy, I ended up with a very complicated shape, right?
But why there is A and B here?
This is some kind of parameter, so this is allow you to tune it, right?
Oh.
So therefore, like if we pick something like a form this one, then like basically after multiplying this, we still have a nice form, right? And for those cases, we call this a conjugate prior. Conjugate prior for this likelihood, and we just go through that like a conjugate prior for in this case is a beta distribution. If this form is actually equal to this guy here, and this is the beta with parameter a, b. The convention is like if you have a, b, this is equal to a minus 1 and 1 minus q, b minus 1. And this is just the normalization factor here.
That you calculate, you multiply this one with this one?
Yes.
Oh, and you get this one?
No. You multiply this one with this one, but this is just, okay, we want to pick a form like this, but what kind of distribution have a form like this? It turns out the distribution is the beta distribution. Yeah. And
after multiply this one and this one, we get this one?
No, not yet. No, this is the this is okay. Just by inspection, we want the distribution pi to be like this, but this is just like what kind of distribution will be like this? What I'm saying, like this is a beta distribution will be like this one. So have a form shape like this, or maybe I put a minus 1, b minus 1 here also if you find this confusing. So the convention here, they have parameter a and b will have a shape a minus 1, b minus 1, but you have this gamma here. It's just like some normalization factor, right? Because if you try to normalize, integrate this with respect to Q, then you should get 1, right? Because this is a probability distribution. So you need to have like some.
So you mean you get this one from this one, but this is in the normalized mode. This one in normalized mode.
This is a distribution.
Yeah, and
you forget about this. This is the conjugate prior distribution.
And that is similar from this. That from there.
Yeah. If you multiply this guy, you see like have the same shape, right?
Okay.
You multiply that, you still have like Q a minus 1 plus k, something like that, right?
That's right.
Yeah, that's what we want. So then we quickly run through what's the gamma function. The gamma function, you don't need to care about the shape, but the gamma function have a very nice property that like gamma c is equal to c minus 1 times gamma c minus 1. You can easily show this. Yeah, just some algebra calculus there. But using this is very nice to use that to find mean and variance, for example. For example, you have a beta distribution, you want to compute the mean. You will be like, this is the beta, right? Have this shape here, a minus 1 time, then multiply by x, right?
Yes.
So I have this x can absorb into this, right? So now it's x to the a here.
Yeah.
And this guy is a constant, put it out here, right?
Yeah.
Now I integrate this guy. This is like basically like a, what I should say, like this thing here is like the beta distribution also, right? And the normalization factor should be like gamma a plus 1 plus b over gamma a plus 1 gamma b, right?
Yeah, something like that.
So if I integrate this xa 1 minus x b minus 1, if I integrate this to get me 1, right?
Yeah.
So therefore I integrate this part alone should be equal to 1 over this guy, right?
Why you get this one? From where you get this one?
This is here. This is
Oh.
this guy here.
Oh, and this one too? Oh, 1 minus x. Yeah, that's right.
Yeah.
So if you integrate that with this one, that you get 1. Yeah, that's right.
So therefore, I integrate this part alone. I should have 1 over this guy, right?
Yes. That's
So
right.
therefore, the whole thing should be
1.
this is just equal to no. This thing is just equal to gamma a plus 1 plus b, right? Over gamma a plus 1 gamma b, right? Integrating this guy is equal to this one here.
Yeah.
And then this multiplied by this, because of the equation we just mentioned, that we have gamma x is equal to x minus 1 gamma x minus 1.
From where then?
From previous page. I didn't go. I went through it, but I didn't go through it just now.
Oh, yes.
So this one you just take integrate. Integration is very easy. You get integration by pi and so on.
So that is the gamma function. You have this one, and you want to put that in the class.
Yes, this equation is very useful. So using this, then therefore this is just equal to gamma a plus b times a plus b, right?
A plus b. Yeah.
So then this 2 gamma a plus b can get cancelled.
That should be same.
Yeah, and this gamma b is cancelled, and this guy also, like gamma a plus 1 is equal to a times gamma a, and this gamma a got cancelled as well. So therefore you get like a over a plus b.
And that is the mean.
That's the mean. So that's what I'm saying. Like if you use this equation alone, it's very convenient that you don't actually need to do the integration, really. So similarly, you can compute the variance by first computing expectation x squared and so on, and
You get that.
yeah, you get that. So yeah, that we were. So let's go back to what we were talking now. Then where is that?
So we already have mean. We already have variance.
Yes. Oh, wait a sec. I erased whatever. So I'm also like we can compute the mode. The mode will be, I just mentioned that. But I erased that. Like if you compute the mode here, you basically have mode is the peak. So therefore, like you just take the partial derivative with respect to x and set it to 0. You do some calculation. It's very simple. X is just equal to a minus 1 equals b minus 2. That's the mode. So we have the mode mean. Okay, maybe just focus on the mode and mean. Mean is very simple. A over a plus b. And mode is like a minus 1 over a plus b minus 2. So we will use that afterward. Now, if now let's try to compute the posterior. So we just mentioned, okay, if we are doing a map estimation or something like that, right? I'm trying to max the Q there. For some observation x, x can be, or like we used k earlier. Okay, x is okay. So this is like basically x outcome. There's x hat here, something like, and the parameter is a and b, let's say. And then I mean the pi parameter, what I want to say.
So you want to maximize the what is mean that?
Maximum or posterior probability.
Posterior,
Yeah.
The maximum posterior.
Yes. And
You have higher.
yes, our prior is given by this, right? QAB. We just mentioned this is a beta actually.
Yeah.
It's a beta. And we have the binomial distribution Px given Q as the likelihood. This is binomial.
Yeah.
And so to be precise, my binomial should be something like what? Q to the x 1 minus Q to n minus x. So assuming I have n flips there. And there's some constant, I don't care actually. It's basically constant multiplied by, this is the binomial, and I have the beta is like, what, Q a minus 1, 1 minus Q, 1 minus Q to the power b minus 1, right?
Why you say constant? Because
that's the normalization factor.
Oh,
Remember, there's a normalization factor, like there's gamma A plus B also, and this has some normalization factor for this guy also.
Oh, yeah.
But we don't actually care about that.
Okay.
So, and you look at this whole form here, we got Q x x plus A minus 1 and 1 minus Q m minus xb minus 1, right? Plus. Yeah. Something like that, right? Now you look at this thing here. In terms of Q here, it's just a beta distribution, right? And
Yes, that's right.
so therefore, like this is actually, that's why what I mentioned, like we don't care about this constant, because by inspection now we know this is a beta distribution. We know what is the constant really. We don't need to, but we know this is basically a beta. Yeah.
Yeah, because we want to maximize in Q, not so constant can be regardless.
Yes, yes, it's true. But actually, let's even forget about this. Just this here, like I can write it down, because you look at this is basically just a distribution of Q here, right?
Yeah.
After all this, I see that this is a form of a beta distribution.
Yeah.
And so therefore, I know this constant factor is what is this actually. Because this is basically is a beta with what? With parameter
Beta A.
is x plus A, right?
Yeah. Minus 1.
No, because it's the form is a beta AB is actually Q to the A minus 1,
Oh.
1 minus Q. There's a minus 1 there.
Okay.
So this guy is and B is basically M minus X plus B, right?
Yeah.
So this is so therefore, like actually I know what was this constant here. This constant turns out is what?
Gamma.
Gamma A plus B, right? So A plus B in this case would be like X plus A plus M minus X plus B. So therefore it's actually M plus A plus B over gamma A is a gamma X plus A, gamma M minus X plus B. So we don't actually need this, but we can actually write down the normalization factor afterwards. So therefore, like we can skip these steps here. We don't need that. We don't need to really try to compute the normalization factor.
Yeah. Because that also there is no. It depends on the Q. There is not.
Yeah. Some, yes. But sometimes maybe will be useful afterward. But in this, most of the time we don't actually need to. In the intermediate step, we don't need to deal with the normalization factor. We just need to check the final form there. We know what form is that, and then we look at what's the parameters for those form there.
Yes.
From that parameters, we can kind of derive back what's the normalization factors. So
That's right.
now, this is the posterior. Now we can do some example here. Just compare, let's say for different cases. So let's say
Yeah, how to maximize that?
we're going to maximize it now. So, but let's see. Let's consider the prior. Okay, beta prior with like parameter 1 1. So I mean like A and B are 1 and 1. So, and we know that for 1 1 was this is actually, for example, Q. This have some normalization factor here, but it's like Q to the 1 minus 1, 1 minus Q to the 1 minus 1, right? So that means like this is 1, this is 1. So what I mean, this is actually basically is just equal to a constant, right?
1. That is 1 minus
Actually,
1.
it's just equal to 1.
Because 1 minus 1.
Yeah.
And that is 1. So
Yeah. A is 1, B is 1, and this is K A minus 1, right? Q B 1 minus Q B minus 1 is supposed to be. This is very hard to write.
So, could you write what is the original? Because beta I do not.
Okay, let's put down the beta again.
Yeah.
Beta Q A B
Yes.
is equal to gamma A plus B, gamma A, gamma B, Q to A minus 1, 1 minus Q, B minus 1.
Oh,
Yes.
that's right.
So therefore, like,
Yeah, that's right.
if we pick A, B is equal to 1, that's actually will just give me 1.
Yes.
If Q beta. So that's the uniform prior. That's basically like we have uniform prior, meaning that there's actually no information. Therefore, like, if we impose a uniform prior to do the approximation, that just give us the maximum likelihood, really.
That's, I think mean is 1 and variance is 1 is not uniform. Why this could be uniform? Because that is mean. This is variance.
No, mean is 1/2.
Yeah, mean is 1.
Mean is 1/2. Mean is equal to A over A plus B.
Yeah, A over S. Oh, yeah, that's
It's
right.
equal to 1/2.
And the variance?
Variance is I don't remember the form. It's a bit more ugly. It's like this, but it should be equal 1/12. Honestly.
So it means that there is variance in there. If
Yeah,
there is
this is variance, yeah.
If there is variance, it means that there is variability. That's right.
Yeah, but that's exactly right. Uniform doesn't mean that like you don't have variability. This is a uniform distribution, right?
Oh, so it means that always uniform for every.
It's just for all.
Every in here will be same.
Yeah.
You already find that. I mean, that you already solve using MATLAB. That's uniform.
No, you just read here. You see it's uniform, right? I mean, you have this A B is equal to 1. You get that it's just a constant. That's what do you define a uniform distribution, right? Just everywhere is the same.
Oh, yeah, that's right.
So let's say like for you, therefore if we use this prior, basically it's just a maximum likelihood estimation, right? So or let's look at maximum likelihood. Let's say if I have in this case n is equal to 10, I have 10 flips here. And let's say I have 0 heads there. I'm trying to estimate the Q. So what's the maximum likelihood estimate?
It's O.
No O, just 0 head, no heads.
Oh, 0 head. So what's the?
What will be the estimate for Q for maximum likelihood? So let's just do it step by step. So if like I can write down the likelihood, right? The likelihood is just like Q to the what a binomial likelihood, right? So I have Q to the let's say the number of counts as Q 0 and 1 minus Q 10 minus 0, right? And I have some normalization factor here. I don't care. I should up max that, right? Up max for Q. So
yes. 1 minus Q power 10.
And of course Q should be in the range 0 and 1 because it's a probability.
Yes.
Yeah. So to maximize that, what was the value to maximize that?
This become 1 minus Q power 10 because this is 1.
Yeah.
And then to maximize that, just
0, right?
Different.
Wait. What's the maximum Q for?
Is 0.
Yeah. Q is just equal to 0, right?
Yeah.
And we can verify that whether if we use a uniform prior, it also makes sense. So because you use a uniform prior, it means that there's no information there, right? So it will be, if you input a uniform prior to compute the map as maximum or posterior estimation, it should be just equivalent to the maximum likelihood. So we can track that. So let's say I should mass Q now, but with a kind of like prior, it's a uniform prior, beta is 1, 1. And then the likelihood is a binomial, have no has here, 0 has, and with with like n cons there, n is equal to 10 here. So then like this multiply them together, as we said, like it should be give us a beta if of Q with what's that? Should be we have that earlier.
Binomial is different.
Oh, of course different.
Yeah.
Beta is a Q to the A 1 minus Q to the B, right?
Yeah. And binomial is.
But you need to be careful. Like, what is the variables here? For beta, the variables here is the Q here. Now for binomial, like when I write like this, I have like have a similar form, right? But maybe I put an x here. Q to x 1 minus Q, like n minus x, I say. And like x is the variable here.
Oh.
Yeah.
This one.
This is different. So.
But Q is same. And there.
Yeah, Q is the same here.
So we can integrate them. I mean, we can combine them.
Yes, and we don't need to integrate here, as we said. Like we can just combine them, like as here, right?
Yes,
so we have like beta is like this with a minus 1, b minus 1, right? And if we have binomial that the outcome like have like x hat here, so then the new a here, it's just like the new a will be just x plus a, and then the b will change to like b plus n minus x, right?
That's right.
So therefore, in this case, I have instead of x hat here, I have 0 hat here. So then like I have a will change from like 1 to just 1 plus 0, and b is like 1 plus 10 minus 0 will be 11.
Why x in here is 0?
Oh, that's okay. This is the assumption of our problem here.
Oh, that's
We
how
assume like we
our head is 0.
0 has the 0 has here, and
why that should be put in the binomial in here? That's because this is binomial.
it's binomial, right? The likelihood is binomial. If you have a probability of hat is Q, I have like x number of hats. I ask you like what's the probability for that? It's a binomial distribution, right?
Oh, yeah.
It's a Q to x 1 minus Q n minus x. I have a NCX here, but I don't care about this actually. I don't, because I only care about Q here,
Yes.
right?
Yeah. And then this is prior.
No, this is prior. This is the likelihood.
Oh, this is like.
Yeah. X is the observation. You have the parameter. This is a P x given Q, right? Q is the parameter that we want to estimate. X is the observations here. But for Bayesian and also maximum a posterior estimation, we also impose a prior, right? Impose a PQ here. And this is the prior.
Oh.
That's the beta.
So why you put in here a beta in normal, not uniform, something like this?
Oh, okay, because we are doing like maximum likelihood estimation. So when you're uniform, you basically impose no information there, right? When there's no information, it's just you're actually trying to only maximize over the likelihood alone. So that the prior should have no effect for this thing. But we see here, like, okay, doing a maximum likelihood, going through the classic case, we get like Q is equal to 0, right? Here I want to verify, okay, if I put a prior, there's no information, and do a Bayesian not Bayesian, maximum a posterior estimation. In this case, it should be just equivalent to maximum likelihood. So we are going to verify that. So then this prior, beta prior, with no information, uniform prior multiplied by this binomial, as we said, is just equal to a beta. With A now is 1, B is equal to 11, right? Now the estimation for Q, if this is a maximum likelihood in this case.
So we should always use something like maximum, like something like this, don't you? For any question.
I don't know what you mean by any question.
I mean that for if this is a different distribution in here for maximum likelihood, so we should use prior this beta.
No. I mean, we will see more example. For example, your you're doing a conflict where you only have like 2 outcomes. So even you're folding a dice, you will have something very different, right?
Yeah.
And then the distribution for your likelihood will be different, and then the corresponding prior will be different as well.
So we should choose any this one.
No, not any, but basically for everyone, I would say like it's not a must, but almost it's a must. It's like people will always pick conjugate prior because it's tractable. Otherwise, you don't know what you can do. So you have to, when you define the likelihood, more or less the form of your prior is specified. You pick the conjugate prior of that likelihood.
So what you say that conjugate prior, it means that this one conjugate with this one?
Yes, conjugate beta is conjugate to the binomial. In the sense that, like, again, like your binomial has a form like this, right? Now you're trying to estimate this guy, you try to multiply this, some function of PQ with this guy here. I want to multiply after the multiplication, I still have some form. Have like Q to the something, 1 minus Q to the something. So then a lateral choice for your PQ would be like something Q to A and 1 minus Q to B, something like that, right? And then it turns out that would be a beta distribution.
So what's the meaning here, conjugate?
Well, again, the meaning for conjugate just means that you kind of, okay. You're asking an English question, or you're asking like what's this definition?
Can conjugate something like A minus BI, A plus BI, so that is conjugate.
No, that's different. Like you have like conjugate like defined in different disciplines, right? This is totally different, like from you have complex conjugate and so on.
So
yeah.
In this one, conjugate something like similar.
No, I'm not an English person. You can take a dictionary, but the conjugate prior is a conjugate is just something complementary, I guess, in this case. You want to kind of matches with your your
like
kind of like your likelihood. So then let's continue this. Like now, if we try to maximize Q, like what's the maximum for this guy?
Yeah.
We checked that earlier, right? We did that earlier. The mode or like the peak of this distribution is A minus 1 over A plus B minus 2, right? So therefore, this will be equal to a 0 over 1%. Yeah. 11 minus 2, that's basically 0 over 10 or just 0. Yeah, that's the same. We just want to make sure. Yeah, that's indeed is the same. And for maximum likelihood estimation, you see like it can be pretty extreme, right? It's saying that if I fold a coin say 10 times, and if I got all of them is a tails, I don't get any head, then I would just conclude that like the probability of getting head will be 0 in the future, right? Because that's basically saying the Q will be just equal to 0. So therefore, if I try to estimate what's the probability of getting head like in the future, it will be equal to 0. So that's why like.
So why could we use another that?
Yeah, of course, like that's what I'm saying. So just saying that maximum likelihood, like we already know that like maximum likelihood can be extreme. So, but here I just, of course, this is like the first class we only went through this. So here I just it's both a review but also like to introduce the concept of conjugate prior here, right? So we have now, let's say if I have a map estimation. Now we don't pick a uniform prior here, but let's say we pick a prior beta is equal to 2m2. So
3m2.
2m2.
Oh, 2m2. That's the.
So for that one, we can go through the same step here. So after, if it's 2m2,
That is uniform.
this is not uniform anymore. A and B is 2m2 and multiply by binomial. Binomial.
Still a little bit.
Uh-huh.
Understand about how to know this unit not uniform or not uniform.
Oh, okay. This is uniform, and only this one is uniform, because you look at like the beta q here. Q when A is equal to 1, B equal to 1. This has a distribution is gamma A plus B, gamma A, gamma B, and this is equal to Q A minus 1, B minus 1, Q 1 minus Q, B minus 1, right?
Oh, so
Right.
that is constant.
It's constant, it's like Q to 0, 1 minus Q to 0, the whole thing is just equal to 1.
How about 2? Will be not.
It won't be, it will be given Q, when A is equal to B equal to 2, it will be Q, 1 minus Q, right?
Yes, that's
Basically
one.
have something like that. You have a form something like, I guess it's probably some form like this probably.
Oh, yeah. In the Q, refer to Q.
Yes.
Yeah, refer. This is Q.
Yeah,
Oh,
this is Q.
okay, I understand.
Yeah. So if you use a prior like this is a prior that we are kind of picking wait two
You want to get maximum.
yes, but we want to say like this prior, I want to comment a little bit of this prior. This prior is basically the first one is like kind of uniform prior. This one is trying to give more emphasis like to the middle, right? Your prior like this shape, we are saying that it's more likely that it's going to be unbiased in this case. So if we have this prior, again we multiply this binomial distribution, we get like the final beta is a beta, and it would be like 2 and 12, right? A and B are 2 and 12.
Yes.
Now if we try to, again like for maximum posterior a posterior estimation, for my estimation we try to maximize over Q there.
Maximize that.
Yes.
The posterior.
And then the mode, again the mode is like A minus 1 over A plus B minus 2, right? So therefore it's like 2 minus 1, 2 plus 12
minus 2.
minus 2. So it's equal to 1 over 12.
Yeah, 1 over 12. So you mean that a different answer?
Yes, it will depends on the prior. It definitely depends on the prior. Actually, this is a much more kind of reasonable one, right? So it's like less extreme in the case. Like for the first one, it sounds like okay, if you get like 10 tails, you will just came like okay, I will never get a head. It doesn't is going a bit extreme. And this one, is you say okay, the next one you're going to have maybe 1 over 12. And another interpretation of this is something like you can think of like.
But in our likelihood is 0. It means that I think we cannot get the head.
Yes, that's exactly. That's why we want to impose a prior, right? If you just look at the likelihood alone, you thought that like you think that it will be always 0. We won't get any head, right?
That's right.
So, but we can impose a prior that make it less extreme here. So this is some kind of regularization, really, right? So make the solution is less extreme.
So how to choose the prior then?
Yeah, that's a tricky question. I mean, yeah, you can say like what kind of form of prior you should pick. Like you should always pick a conjugate prior, but what prior you should pick is a little bit tricky. Or Or like, of course, you can make the prior also a a variable as well. So you can put a prior to this prior beta, and then but of course you think Q is also a distribution, a prior of this beta. Then for this prior distribution, we'll have some parameters as well. So you will have a hyper prior parameters, and so on and so forth. You will have, I mean in general, like, what I mean is you can try to make Q also I mean like for A and B, right? A and B is some parameters, right?
Mm-hmm.
A and B, I can make A and B also some kind of random parameters. Like, yeah. For example, I can pick A and B is a distribution of, I don't know what should I pick. If I Gaussian, probably is bad.
Mm-hmm.
So I need to pick A and B as a hyper prior. Sorry, conjugate prior of this beta.
Mm-hmm.
Now probably I need to take up Wikipedia. I don't actually know what's the conjugate prior for beta on top of my head, but yeah, but you can do that.
So how to measure confidence that is the true outcomes if we have that like that? Okay, for this one is 1 for 12, this one for 0. So what is our confidence? This one or that one?
No, I don't.
It's all of this true actually in the calculation, but how to measure confidence?
In this simple example, I guess it's difficult because, as I said, like this prior here is arbitrary. Like you. But I can comment on the one interpretation, like what we are doing here. Actually, what we are doing here is basically saying, in the first case, we just assume that like okay, we only focus on that 10 observations, and for this second case, it looks like we are assuming that like before the experiment, we did toss the coins 2 times already, and we toss the coins. It turns out like one is head, one is tail, and then we include that as part of the experiment.
Yeah.
Yeah.
That
So
we have another information.
yeah. So, but which one you think make more sense? Okay, this will be a bit extreme. Probably it's not. Does not make any sense. But you can also claim like why only toss 2s? Why not toss like 4 and then like, I have like 2 head and 2 tails and then. So this is your choice. So therefore, like it's kind of I don't know how to answer you because this is I don't think has a very good answer like what. But of course, you can change and try different priors, or as I said, like potentially you can even go with a kind of like of this A and B parameter to make them as a kind of like a variables as well, and then I will impose another distribution on top of these parameters.
Can we do this as training? It means that okay, we have some testing, and this is as training, and we can compare this one and this one. Oh, so we can find the prior is good, something like a neural network.
Yeah, sure, you can do that. Like, if you have enough data, I think like you can do that.
Yeah, so we can find what is the best prior in.
Yeah, you definitely can do that. But let me continue. Like, also look at the Bayesian estimate. So for the Bayesian estimate, so let's say like for Bayesian, let's say I use the original prior, I use the non-uniform prior like Q11. So if I use the uniform prior, now let's look at the Bayesian one. Uniform prior with beta multiplied by binomial. Again, I should got a beta Q1 and 11, I think. Now, but here I use a Bayesian, so therefore like instead of like max this guy, I'm trying to compute the expectation of that way. I'm trying to compute the expectation of Q for Q as a beta, right?
So you want to find the mean.
So this is basically just a mean, and we already computed what's the mean. Mean is like A over A plus B, right?
Yeah.
So therefore it's just, again, it's 112.
112.
So I mean, using Bayesian is kind of self-regularized. So even though you have the prior can be pretty extreme, like in the first case, it's still like the maximum likelihood uniform prior that doesn't give any information. Once you use Bayesian, your solution will be kind of less automatically regularized. Regularized. So
What do you mean?
regularized meaning that like the solution is will not go to the extreme case. Yeah.
But this one is also extreme case?
No, it's not. That's what I'm saying. It's not yeah, because why it is so because when you use Bayesian, you're actually looking into all the different combinations, right? For this guy, you're only taking the most probable one, and this is actually doing kind of like an integral, right? We're taking like for different possible value of Q, and then we sum over that. And that is kind of like some kind of averaging effect here, so making the solution is less extreme. So, but yeah.
This one is one, comma 1.
Yeah.
So this is actually as prior, our prior
Yes, we again I use the prior for uniform.
from uniform.
Yeah.
And then when we get the expectation of this one,
Yeah.
expectation of this one,
Yes.
so we find that 1/12.
Yes.
So different with the only 0 there.
Yes. Yes. It's different. As I said, we are doing a average. For Bayesian, we are doing an average instead of like doing a the maximum values. So, and if you're looking at the average, it will give you a less extreme result than just looking at the maximum value.
So it's really, yeah, it's really even every, how if we put in here 2 and 2, what the result?
Yeah, you can check that. Like if I have two here, then I will have like the final one is like beta Q 2 and 12, right? So the average is basically 2a over a plus b, or a over 2 over 14.
Yeah,
So it's 1 over 7, something like that.
that's the difference, one also
Yeah.
expectation. Okay.
So your pi will affect your final estimation. Yes. And so let's look at a couple more examples. Let's look at say let's say we have floating dice. In that case, you have like more than one values, right? So then we will have a kind of multinomial distribution. So basically, for example, if I have dice, I have like 6 probability P1, P2, up to P6. I have 6 different probability. And then like I have a particular outcome, let's say. Yes.
Question for the previous, so what we should pick up in there? The expectation number or no?
Actually, when you can, I think it's better to use Bayesian.
Bayesian,
Yeah.
not expectation.
But when you're Bayesian is doing the expectation, you're using the mean.
Oh.
But what I mean is like, I'm not sure always the calculation is easy, right? So, but if like in this case, is your closed form and simple like Bayesian probably is better than like doing the maximum likelihood.
Maximum.
Yeah.
But the before one is maximum likelihood. That is
Yeah.
maximum a posteriori.
Yeah.
And the second one and the first one is maximum likelihood.
Yeah, it's a maximum likelihood. Yeah, it's maximum likelihood. But here we also show that okay, this maximum, we can also like consider this maximum likelihood problem as a map problem, right? But impose a prior that's a useless prior. Basically, the prior doesn't have information there.
Yeah.
Then a uniform prior. Then this is still a kind of maximum likelihood.
Yeah. But in the Bayesian actually same with MAP, but in the expectation, the
Actually, I'm not sure. Like in this case, I probably it's just lucky. Like this turns out to be the same. I don't think in general they will be the same.
But,
And also like you have a different prior, right? Because
but there is this one calculation in Bayesian, the averaging.
Bayesian is for the maximum for the map here. You don't do the maximum. You don't do the averaging, right? You do the maximum, right?
Yes.
So they are not the same.
Yeah.
You said like they.
Yeah.
You said like they.
Then, this one actually same with this one, but in here there is this calculation. That's right.
Okay. I guess don't try to overinterpret this curve equality of these two values. I guess it's just getting lucky.
Yeah, that's getting lucky. It means that I just I want to see the calculation. This one and this one actually the same. Just in here there is expectation calculation.
It's not the same. Here, I just for map here I pick a pi that is informative.
Yes.
I didn't pick a pi. Okay, I mean the pi here. I didn't pick a uniform pi. Let's say I pick a pi like if a and b equal 2 and 2.
Mm-hmm.
Now it turns out the value I multiply the posterior probability say with like a and b is like 2 and 12, right? Now I find the maximum. I find the mode here. It turns out the mode is equal to 1/12.
That's right. That's right. Meanwhile, in here, you find this extreme. You use that.
For here, like I use the extreme case.
And
I just want to demonstrate that even I use an extreme case, a uniform prior, I still get like a not very extreme estimation.
Yeah. So it means that in the Bayesian, we can put any not extreme. You can also put this
Yeah,
one.
Bayesian, yes. Yeah, you can put whatever prior into that, but like what I want to demonstrate is that even you put a pretty extreme prior, you still get like something is not too extreme.
But the important thing should be there is expectation calculation in the Bayesian.
Yeah, in Bayesian, you should use the expectation.
Okay, I understand. Thank you.
Yes. So okay, let's look at the dice problem again. Go back to this one. So let's say like I fold the dice n times here. So let's say I have have a dice have 6 outcomes, right? So therefore like I can have like x1 is a number of 1, x2 is number 2, and so on up to x6 here. So therefore like x1 plus x2 and so on, they should sum together equal to n. I have n flows here. So then I can define multinomial distribution.
X1, X2 until X6 is the outcomes.
Yes, the outcome.
So why you want to sum this one? Oh.
No, they should add up to n.
Oh.
They have like I fold this n times, right?
Oh, okay.
So let's say I have the observation is x1 and x6, and my p1 and p6 are the probability of getting each of the outcome, right? Then this will be just equal to p1 to the x1, p to x2, and so on, right? p6 x6, right? And there's some normalization factor here. It's basically n factorial over x1 factorial, x6 factorial, something like that.
That's the
Normalization factor.
normalization factor.
Yeah, this is like less important. The important is this part here.
I mean, why you form that?
This is this is the probability of getting 1, right? Probability of getting 2 and so on, right? So you have like number of 1 is equal to x1, right?
Yes.
So therefore it will be just the probability of getting x1 so many 1 will be just p1 to the power x1, right?
Oh yeah.
So then you just multiply all of them together.
Something like the previous.
Yes, it's similar, but it's just I have more outcomes here. And also of course like p probability, so p1 plus p2, so on, plus up to p6 is equal to 1.
Yes.
Right? Now we need to define what is the conjugate prior. So we want to estimate, for example, the p, right? use P here. It's a little bit, it's okay. Hopefully it won't confuse you. So I want to estimate this P, right? Given observation x1, and also maybe some parameter, theta, there's some pi here. So I have like basically P, P1, P6. Sorry. Let's write the likelihood first. X1, X6, P1, P6. That's basically this guy here, right? The multinomial distribution.
Yeah.
And I have the prior.
The prior.
It's like P1, P6 with some hyperparameter theta, let's say. So we need to decide, okay, what kind of distribution will be kind of conjugate to this like multinomial distribution.
This is the prior, and then.
Yeah, this is the prior.
So why you put theta here?
This is like you want to have the prior. You don't want to have like just a fixed one single prior. But as in the previous case, you want to be able to tune that way, tune the prior. So you have some parameter. That's like the A and B in the previous case here to tune the parameter.
To make tune.
Yes.
Okay.
So and this again, this is a have a form P1 x1 right, P6 x6 right. So what we want is we probably want to have like something also maybe have format like P1 A1 and up to P6 A6 right. Something like that. If we have a form of distribution like this, then will be a conjugate prior of this multinomial distribution.
But why there is no P here?
Oh, you mean theta?
Yeah, theta.
Okay. In this case, theta will be this A1, A2, A6, something like that.
Oh, this one A.
Yeah. So now we want to know what kind of distribution for this conjugate prior. It turns out like this distribution is known as the Dirichlet distribution. Dirichlet. So short for DIR. So Dirichlet x1, xn in general with parameter alpha 1 up to alpha n. Those are the features I mentioned earlier. Theta just and this is equal to x1 to the alpha 1 minus 1. It's very similar to the beta. We have a minus 1 here. Previously, we have like a minus 1, b minus 1, right? I mean, for the beta distribution, we have like q to the power a minus 1, and like 1 minus q to b minus 1. Here also the convention, we have this alpha minus 1 here also. So x2 alpha 2 minus 1.
That is in here is wrong because I mean that the x minus 1 is come from where?
What, this alpha you mean?
I mean that no, x minus 1 here, x power minus 1. So this component is come from where? Okay, maybe that's just make some modification on that. Alpha is minus 1, should be minus 1.
It's a convention, like they use alpha. I guess the distribution is easier to write like this. Of course, if you define the other way, it's okay to, right? But this is the convention how everyone do that.
Yeah, because we can put any here.
Yeah, if you change here, then like the normalization factor will change, right?
Yes, that's right.
Yeah.
Yes, so that we can put any that.
Yeah. Alpha n minus 1. The normalization factor is like gamma alpha 1. That's up to alpha n over gamma alpha 1, gamma alpha n. So as I said, like if you don't want this to be alpha minus 1, but then you will just have this plus 1 here, right?
Yes, that's right.
The convention is that people like to write it this way instead of, right?
Oh.
So then they just put alpha minus 1 here.
That's right.
So, and this is the Dirichlet distribution, and like previous case, knowing the form of Dirichlet is like this, knowing the normalization factor like this one will help you a lot in computing, for example, like mean, mode, maybe just mean and variance and so on, or the moment. For example, like if I want to compute the mean for Dirichlet, the expectation of like just x1, let's say, it will be equal to gamma alpha 1 alpha n gamma alpha 1 gamma alpha n x1 alpha 1 minus 1 x2 alpha 2 minus 1 and so on, xn alpha n minus 1. But I should have x1 here and multiply by x1, right?
Multiply by x1
dx1. We should integrate with everything, but integrate over everything.
Oh, that's right.
But the point is that it doesn't matter. Again, I can absorb this x1 into here. So instead of like
so this one will be regardless in this
like
integration.
This,
yeah.
Like that. Now again, I integrate this part. It should be equal. This is again have a form very similar to a Dirichlet distribution, right? But without the normalization factor. So therefore, integrate this part will be equal to 1 over this normalization factor.
So sorry, where it come from this one? x1 come here, so become x lambda 1, x
1 to the alpha 1.
Then this is this
Yeah,
pair.
minus 1 I got erased, right? Yeah.
So
then like this one is very similar to the Dirichlet distribution. With like parameter will be alpha 1 plus 1, right? Plus 1. And the rest is the same, right? Alpha 2 and alpha n, right?
that's right.
And so therefore, like if I integrate this part, should be equal to the 1 over the normalization factor of this.
1 over.
Yeah. So therefore, like actually this integral should be equal to gamma alpha 1 plus 1 plus alpha 2 plus so on up to alpha n. And the numerator should be gamma alpha 1 plus 1, gamma alpha 2, so on up to gamma alpha n.
Oh.
Yeah.
This is the standard Dirichlet integration become this, and because this is there is no 1 here, so this become 1. Okay. You put add 1. You add 1 in here.
Yeah, this is alpha. Yeah. This is a parameter with alpha 1 plus 1, right?
Yes, that's right. And become there.
Yeah, that's for alpha 1 plus 1 here. So then, like again, like this alpha 1 gamma alpha 1 plus 1 is equal to alpha 1 times gamma alpha 1.
Yeah.
So then, like for the rest of this guy, all of them got cancelled here.
Alpha.
And gamma
Alpha.
Yeah, I'm gamma. Yeah, I'm only have alpha 1 left behind, right?
Yeah.
And similar for this guy.
Also can be cancelled.
Yes, I only have like alpha 1 plus alpha 2 up to alpha n left behind, basically. So therefore, eventually, this is just equal to alpha 1 over alpha 1 plus alpha 2 up to alpha n, something
Yes,
like that.
that's right.
And you can do more or less the same thing, for example, to compute expectation x1 square and high moment. And it actually will give you something like alpha 1 plus 1 times alpha 1 over alpha 1 plus alpha 2 plus alpha n plus 1 alpha 1 plus alpha 2 alpha n. And then you have the second moment and also the first moment, the mean. Then you can compute the variance just as the expectation x1 square minus expectation x1 square. So this is just equal to, if you do some computation, you can do alpha 1, alpha 0 minus alpha 1, alpha 0 square, alpha 0 plus 1, where the alpha 0 is the sum, alpha 0 equal to alpha 1 plus alpha 2 plus alpha n, something like that. Yeah.
So This one also can be like that. Alpha 0 is total set.
Oh yeah, I can write this as alpha 0.
Mm.
And wait.
And when we want to find alpha, basically.
It-
We want to find
no, actually alpha is the hyperparameter.
yes,
The pi parameter. So we want to find x here. Where is the x? Let's see. What is the? We want to find, in this case, for example, we want to find the p here, right?
Yeah.
So we have alphas are all the theta here is the hyperparameter.
Yes.
Well, actually, we let's take a break. I don't know. Let's take a break for
Yeah.
15 minutes first and come back.